Let's talk about the definite integral, okay? Now, before we approximated the area under a curve with a Riemann sum. So you had the sum as I went from 1 to n, f of xi star times delta x. And remember, this was really just the areas of rectangles, right? So this first number here was the height, and this second number here was the width. And then what we did was we multiplied those together to get the area of a rectangle, and then we added all those areas up. So now we're ready to talk about what a definite integral is. So let f of x be defined on a closed interval. The definite integral of f from a to b is, leave a little bit of room on the left, and let's first write our Riemann sum in the middle over here. So we got the sum as I goes from 1 to n. We got f of xi star times delta x, okay? And what we're going to do is we are going to take a limit. We're going to take a limit as n goes to infinity. And the effect of taking the limit as n goes to infinity is twofold. The first thing is that this delta x, this width, becomes incredibly narrow, infinitesimally small. The second thing is that it's not going to matter what xi star is. It doesn't matter if I use the left endpoint or the right endpoint, because this delta x is so narrow that those two endpoints are virtually the same. Okay. Now we don't write this notation for our definite integral. Instead, what we write is this. Remember, sigma was the Greek letter for capital S. So we put a capital S like this, elongated capital S. Then we put f of x. Remember, delta was the Greek letter for d, so we put dx. And then we'll put an equal sign. Now I want to indicate that this integral, the interval goes from a to b, so I'm going to put an a here and a b there. And this whole thing is the notation we have for a definite integral. So this definite integral is this object right here, and the way that we calculate it is by taking the limit of Riemann sums. So let me write down a few notes here. First of all, the definite integral, this is the area under a curve from A to B. The second thing I want to mention is this is the limit of Riemann sums as n goes to infinity. Okay. This number b at the top, we call this the upper limit of integration. And this number a is the lower limit of integration. Now, if this limit exists, the function is said to be integrable. All right? And the variable of integration is known as a dummy variable. And it has no impact on the computation of the integral. Another way of saying that is the integral from a to b of f of x dx. You didn't have to call it x. You could call it the integral from a to b f of t dt, or you could call it the integral from a to b of f of r dr. The actual variable doesn't really matter what name you give it, and the result is going to be some number. Now, when we see each other again in class, we will work on example 1 together. I want to scroll down here and I want to look at what I've written up here above example 2. So let's unpack this for a little bit. This interval going from A to B, this is our region of integration. And remember last time we talked about creating a regular partition. So we have a bunch of points inside. These points are all equally spaced, and my generic interval is the ith subinterval right here. I wanted to really help describe how we can find delta x, describe what xi minus 1 is going to be in general, and describe what xi is going to be in general. So we talked about delta x before. Delta x is just going to be b minus a all divided by n. So this is the width of the subinterval, of all the subintervals, because they're equally spaced. It's a regular partition. Okay. What's more interesting is this xi minus 1. So before we talk about what the xi minus 1 is, maybe we should talk about what the xi is. That would be easier to look at first. So what we're going to do is we are going to start at our starting point A. So let me write A over here. And then what we're going to do is we're going to add the widths of subintervals. Okay, so if you wanted xi over here, then what you would need to do is you would need to add the width of I separate subintervals together. So xi is going to be A, your starting point, plus we're going to have I times delta x. And if we add I delta x's, that's going to take us, we're going to start at A, here's the first subinterval, the second subinterval. When we get the ith subinterval, we're going to be able to grab this point. So how do I grab the xi minus 1 point? I just go one fewer width. So instead of going I widths, I'm going to start at A. I'm going to add what I get when I go I minus 1 widths. And having our handle on these three formulas will make it easier when we look at these examples of the definition of a definite integral together in class. Okay? All right, everyone. Take care.